So up until this point, we've been talking about masses on springs, and we got to an equation of motion for masses on springs. But I want to take a little bit of a detour and really stress that what we're talking about right now is coming from mathematics, and it's actually true for all simple harmonic motion. So any time that you have an equation of motion that tells you that the second derivative of position with respect to time is equal to negative c times position, that is by definition simple harmonic motion. That this differential equation is always going to be solved by a sinusoidal or cosine form. So if you have this, you have simple harmonic motion. So in this form, c is a constant. It doesn't depend on position, it doesn't depend on time, and it's actually going to come from the physics. So we'll look at different types of simple harmonic motion and what c is. Note that the minus sign here is essential, that this would be solved by e to the x if you didn't have this minus sign. So the minus sign tells you that it must be sinusoidal. So once you have this equation, it is definitely solved by this. And in this case, I'm using omega because that's the physics variable we use. But again, c up here was already expressed in terms of some physics constants coming from what the specific problem is. And omega is always going to be equal to the square root of c. So whatever you had here, square root of that is omega. So another way that this gets written is that it is equal to negative omega squared x. But the point being, when you first see this equation, it won't be written as omega, but whatever's here is actually equal to omega squared. Now in this equation, a and phi naught are defined by initial conditions. So again, where is it? What is the initial speed? So the equation of motion isn't telling you what those are, but the system tells you the equation of motion. Your initial conditions tell you a and phi naught. So let's now apply this to our mass on a spring. And again, initially we talked about how it was solved by cosine, but I had pulled that out of air. And now we are talking about mathematically where that's coming from. And again, this equation was coming from the ideal spring, Hooke's law, and Newton's second law. So if this is our starting point, I recognize this form. Once I recognize this form, I use differential equations to write down the answer. And I see now that for a mass on a spring, c is equal to k over m. And again, not with the minus sign because the minus sign is explicitly out front. But so c is equal to k over m, and we said that omega is equal to square root of c in this case. So now my angular speed, my angular frequency in this case, is square root of k over m. So this is coming from whatever my situation is. Again, the spring constant and my mass. It is independent of how it started. So again, this is just from the system. And we said that earlier when we used conservation of energy. And again, at that point, I was using this cosine form without really justifying where it came from. But conservation of energy also said that how you start your system does not impact capital T period or omega. So this comes from your system, and then a and phi naught are your initial conditions. So we've now shown that this equation of motion, where again, that's kind of a technical term for this differential equation, tells you now this relationship between between position and time. And this was coming from ideal spring and Newton's second law. So anytime you see something in this form, know that it's simple harmonic motion, write down the answer, and then use this relationship between whatever the physics is giving you and this general form to figure out what your angular speed is to then plug in here. So again, look through the book. The book also goes through this process. It might seem more overwhelming if you haven't studied differential equations before, but again, you really don't have to do more here than pattern recognition. When you see something that looks like this, and again, x could be y, that really doesn't make a difference. Once you see something that looks like this, you know the answer is this, and by seeing what c actually is in your equation, you know what goes here in place of omega.